from IQC, Debbie Leung.
Thank you. Can you hear me okay through the mask? Yep, good, thanks. So this is on rate-distortion theory for mixed-state quantum data compression. Oh, sorry, forgot to say that thanks to the organizers for a lovely meeting and thanks for inviting me to be part of it. So very happy to be here and having very good interaction. This is my first meeting post-pandemic, so glad that you glad that I'm able to hear. So this is joint work with Sarah Kenyon and Kodai Kuroiwa. That's the bulk of the work that I will describe. And I will mention some small amounts of work from something earlier with Enro and Dave Touchette. In fact, I was planning to talk about this result 4 years ago, but I didn't in the end because I did not make the slides. So finally, it's good full circle that I managed to do it. And a little bit of warning in advance. I told one of the participants that this has been something I have been working on. The feedback I heard was that, oh, rate distortion theory is boring. I agree. I full-heartedly agree. So this is how I will make an analogy. This is a little like running instead of playing soccer. Soccer is exciting and fun. This kind of work is a little like running. So it's very good for you. It can be a little boring. And when you're tired, you should go a little slower. So if I'm too fast, there's something that you just didn't hear me, or there's something that is missing because it's a big gap between this audience and the kind of information theory community. Please do ask questions. Just like running, there is no fixed distance I have to go through. So I can keep my talk pretty flexible length. So make sure that you ask questions if something doesn't make sense on the board. So then I'll start with the first concept of an ensemble of quantum states. It's a very natural idea that you have some fixed set of states. By the way, everything is finite dimensional in the talk. Matrices are the same, like there's no subtlety, no sister algebra, none of that anywhere. Everything is finite dimensional. So, and so without loss of generality, you can even think about this as a finite set. And for all purposes, these guys live in system A. These are density matrices that I'm writing down. And these are the classical labels. Then the experiment goes by someone drawing one of these labels X at random, and the label X occur with probability Px. So these are just probabilities. And then afterwards, if that's a good experimentalist, they will write it down in the system X. And also, they will prepare the density matrix state, rho X, in system A. So this person can be a student of one of my experimental colleagues at IQC, one of Christopher's students, for example. Any question on this physical process? Yeah. Draw a classical random variable according to a fixed distribution. So Px is known up front. This list is known up front. Then draw the random variable, prepare the state. Transmit it in the end. But let's first write down physically what is the state corresponding to this. My apology for using rho for a state, and sometimes they are not the same state when I use the same label rho. I hope the context will make it clear when I add the subscript. The subscript would clarify the context, what that is referring to. So I will write that the state on the system X and A combined is sum over X, Px, have the label in system X. I use the bracket notation most of the time. Tensor, rho X living on system A. So now this is what we want to do. we'll repeat this n times. So then you get this particular state. Because this, when we draw it n times independently and identically, the probability to get a string of outcome x1, x2 through xn is the product probability, px1 times px2 and so on. And correspondingly, you have these n density matrices, these n states on the n quantum system. I just call it a1 through an, so that I remember which one is which. And the overall state is rho tensor n. So with quantum data compression, what we want to do is imagine a situation in which the referee is holding the recollection and what stage have been prepared. The sender, Alice, is given the quantum states, the rho x1, rho x2 through rho xn, in system a1 through an. We will discuss whether she knows these labels or not later. But for now, she doesn't. She only has these quantum states. The goal is for Bob, at the end of the day, to be the one holding those states. So it's just sending those rho x1, rho x2 from Alice to Bob. And just for the sake of trying to be careful, I relabel the system as B1 through Bn. So that's the goal. We will also need to discuss what approximations are allowed. So any question on the setup so far? Now that's the goal. I'll use a different color for the method. So roughly speaking, Alice is allowed to encode the input. Of course, the encoding map has to depend on the block length. This number n is called the block length. She would then transmit a message to Bob. So this is a TCP map spitting out a quantum system M, the message system. And Bob will decode. The rate, the communication rate is 1 over n log base 2 in this talk, the dimension of m. So throughout I'll use this symbol for the dimension of a quantum system. And the goal is to perform this task while minimizing the communication rate. So now there are varieties to this basic setup. So it's ordinary usage. It's not mathematical usage. Variety. So the first one is you can allow side information for Alice. So this comes in the form of another n system that she is allowed to use for her encoding map. And let me write down what that is. So they will be in some state. So for every label x, they correspond to a particular j of x in the side information system that Alice can use to do the encoding. And so these are also just following the label we have in the experiment, what label has been drawn. And there are two extreme cases of side information that has been heavily studied. So the first one is called visible compression. In that case, equals to x. So Alice, in visible compression, is told what state she's compressing. In the opposite extreme, in what we call blind compression, she has no information on the state being compressed. So the two extreme. And what we have been doing in our work is to use a more general setup that includes both. But we'll describe special results when we need to make the distinction. Then the second variety you can consider is entanglement. So Alice and Bob can share entanglement in advance. I'll call this system A0 and this system B0. In some settings, they may regenerate the entanglement in the end. The entanglement rate, so we'll have to distinguish between these two rates now, is 1 over n log A0. So there are three settings you can consider again. The two extremes are the fact that it's free. So you don't limit the size of A0. Then we call this assisted. Or there's no entanglement allowed. So A0 has dimension 1. It's unassisted. So limited. And then you can consider anything in between. You just have two rates in that case. I hope so far any questions so far?
Absolute value is the square root of A star A, right? Or
again?
the absolute value is these are all maps, right?
No, this is the dimension.
Okay.
Yeah.
And the other condition also makes sense. It's just over here.
Yeah. Yes. Well, it depends on which community you are in. I was actually preparing the whole talk with the dimension there, but then when you write functions of the dimension, it becomes a mess.
That's fine. That's good.
Yeah. So now, after all that, you may want to see an example of how this can even be done. So let me introduce a even more complex, ambitious task. It's very heavily related to data compression, but it is a little fancier. It's called quantum state redistribution. That's due to Devertek and Yat, 2008. So in this particular setting, there are three parties. Alice and Bob sharing some mixed state. There is a referee holding the purification to the mixed state. It's in the ID sense that there are n copies of a certain state. And the point is that Alice initially has two systems, T and Z. At the end of the day, C has to go to Bob. She's still holding T, and Bob has a system Y at the beginning, and he's still having the same system Y in the end. State redistribution going to Bob. Okay. If anything from this talk, I think this may be the most interesting spot because this is a very important modern result that gives rise to a lot of useful development. So now this is again, the white part is the goal of the task called state redistribution. And I'm going to use orange to show you the protocol that will do it. Alice again have an encoding map that include, so the important thing is that they share entanglement. A0, B0. So Alice make an encoding map on the three systems combined. Again, a message system will come out and be sent to Bob. So at that point, Bob has three systems: his entangled system, his original system, and the method. So he put a decoding map that takes all three and spit out the thing that he already has and the thing that he should have at the end. And in this framework, just as an aside, they can, in principle, recycle entanglement. So Alice will output an A1, Bob will output a B1, and so they can, in principle, have, at the end of the day, some good entanglement in the end. And the goal is that this should be approximately this date. So the result they have is that this process will have global error in the most stringent sense, trace distance between the output and the input, if so possible. The rate. If the communication rate is at least half the mutual information between the reference Z and the communicator system C, condition on Y. And if the communication plus entanglement rate, I should say communication rate plus entanglement rate, is at least the conditional entropy of C given Y. Now, I won't bother defining the conditional mutual information and entropy because when I want to use this setup for data compression, Bob has nothing up front, so Y is trivial for my problem. So I don't want to waste time on that. So Y equals 1 for quantum data compression. So then it's just the ordinary quantum mutual information between Z and C, and then the entropy on C. That will be required. Okay. Any question on quantum state redistribution?
Just one. I mean, first of all, that's of course a simple model for one-way quantum communication, right? As a general picture.
Mm-hmm.
And then you are requiring that you achieve that rate, or you know that you can. That I don't understand.
Right. Sorry, I should.
You want that rate to achieve, or you win, or I just. What's the goal?
So what they prove is that this task can be performed with vanishing error. If and only if the communication rate is at least this big, and then the combined communication and entanglement rate is at least this big. So that's the statement of the result.
Very good.
It's a really nice result. In particular, it is reversible. That's another really nice thing about it. But what we need it for is something much simpler because Bob has nothing with him up front. So I have some plan to get the bots right, but I get really intimidated after a few people said that it's actually not so easy. I'll try to leave those two up for a while.
When they worked and you're cleaning, they found a protocol which verifies that, or
Again?
they found a protocol or some configuration which, I mean, the down-up implication means you have to somehow construct the channel, right?
It is constructive. Yes. The way they prove, so there are two sides to prove. That you have a protocol that will do it,
And then you cannot do
and
it.
then you have to show the what we call the converse, that you can't do better. of course, if what you mean is whether it is a randomized construction or not, yes. I suppose some form of de-randomization should be fairly straightforward.
Does it use embezzlement?
No. No, so yes, one thing to mention, that these are standard EPR pairs. And I think, roughly speaking, it involves applying a random unitary at some point, according to Haar measure. That, in the minimal, can be de-randomized to a 2 design,
Okay.
which is is smaller than a random Clifford. But whether it can be further de-randomized or not, I lost track. So, examples of quantum data compression. So the example 1 is to use a big hammer. Just take state redistribution. Now, one small thing we need to do before we apply that result, shouldn't have pushed the board up. We still have a mixed state description here. So we need to purify the system. This A1 through AN is in this row X1, row X2, and so on. These states are mixed. That's the whole point about our work. So we purify each row X on A is purified to some psi X on RA. So that's what we do here. So we have R1 through Rn to do the purification for the state itself. And then this label, classical label, is also a mixed state. So you need to purify that too. And the purification doesn't look too bad. Maybe I'll try to climb it in.
So this all goes into your Z, right? What you're adding now.
That's right, that's right. So yes, you can start matching how you want to use it. But the purification first has a form, sum over X. So I'm purifying row here, just one copy for now, and then you can do the tensor yourself. So we sum over X. We have an amplitude now instead of the probability. We have an X on X prime, X on X, Jx on J, psi X on AR. And when we trace out R on psi, then you get that row X. And so the way we can just apply quantum state redistribution is to identify the pieces. T is J, there's no Y. C is A, and then Z is X prime XR. So we can do it with rate no more than half the mutual information between, you can call it A, you can call it B, you can call it C. They're going to be all the same. Just write A there at this rate. And then there's an entanglement rate. Throughout the talk, I'm not too concerned about entanglement. Just assume it's free if you want to. The second example is the original Schumacher compression. In that case, it is unassisted. There's no entanglement given. There's no psi information. And the communication rate is that of the piece that has to be communicated. And that is sum over X, Px, rho X. So you take the ensemble of states, you look at the average state, look at the entropy. That is your rate to use Schumacher compression. Yeah, I mean, historically that's wrong. I mean, he did it first. It's a very nice protocol, but I need to define both, so I just define one this way. Now, the point is that this rate is optimal. If these states are pure. And surely it is not optimal when the states are mixed. Just an example. So to see that it doesn't work for mixed state, take your favorite ensemble, say equal probability, attach garbage. The maximally mixed state I over D has nothing to do with the state. It's just there. It's just there to pump up your entropy. So this ensemble, you should be able to compress it down to one qubit per copy, but the log D is there to cause you a problem with that rate that was written down. Okay? So we know that this expression does not work for mixed state. So in a slightly more refined way to understand what's wrong with the expression, consider these two states. Actually, I don't even need to make a correction. It's so unreadable that it looks like a 5 too. 5. So if you look at these two states, that Alice has to compress. There is never any reason to send the omegas. Because if you have the first system, you can generate it. Condition on 1, you generate omega 1. Condition on 0, you can generate omega 0. So in the least, Alice should discard this last system before trying to compress. So there are names for this. This is called the classical part. The middle one is the quantum part. And this last part is the redundant part. So in around 2001, Kawashii and Emoto developed a method to rewrite any ensemble into this form. It's an algorithm that you can run on your ensemble so that you can maximize this decomposition, that you cannot refine it further. So you have maxed out how much is redundant. You can also extract everything that is classical. And then the rest you can't compress further. They are the quantum parts. And it's a well-defined process. And then the optimum rate, I won't even write it down here. So the way the optimal thing to do is to send the first piece through a classical channel. You do data compression of the classical message. Send the middle one through using Schumacher compression. Throw away the last one. That's optimal. Now, if you don't have separate classical and quantum channel, you only look at one combined communication rate, you have no choice. You send the classical data through quantum channel as well. There's no saving there. There's no entanglement. You can't do super dense coding. So you see the first example of a theme here. So it looks like we can do better. But the best thing we can do is not a lot better than what we already have. What we have done is to remove an obvious problem. So we distort. So at the encoding level, Alice turned her ensemble to a new ensemble. which has less cost, which has a less smaller rate, and then perform standard data compression on the new ensemble. And then the optimization involve finding the new ensemble that has the least rate. So it's not ensemble. Let's So just a two-step process. Distort the ensemble. It has to be something that Alice can do. In this case, that's discarding the redundant part. And then perform standard thing, has vanishing error, you know the rate, and then optimize the distortion. I'll do one more example of the standard results. So when you don't have entanglement, but you have side information that is complete, in the visible scenario, how well can you do? If the states are pure, you can't do better. Just state it verbally. But if you have a mixed state, there is a small little trick that seems to be useful. So, so Alice then knows X. What she will do is that she just throw away the state given to her. It's not very useful anyways. And then she replace that rho X by what we call an extension of the state. So a state is an extension if you have this relation that you can trace A prime sigma x a prime give you back rho x on A. It's a little counterintuitive. She's supposed to send x, rho x, in system A, and instead, she sent something bigger. She sent a sigma x on two system A and A prime. But remember that later on we do Schumacher compression that look at the entropy of the average state on the ensemble. Now, why would getting a bigger state reduce your entropy? It's not so surprising because if you have a mixed state, you look at the purification, which is an extension. You have low entropy when you look at the purification. Of course, in the end, you still have to mix up the state in the ensemble. So it's not so clear how to play it, but in principle, you can. And so it is known that, I should say that the extension has a particular form, which will be useful for the open problem. You can think about it as taking the original state, rho x, and then you purify it. So I'll just call it the purification of rho x A to AA prime prime. And then you apply a channel from A prime prime to A prime. Then you get an extension. And all extension can be written in that form. So the optimization over the extension can be thought of as optimizing this channel. And so it is sufficient to communicate with this rate. You minimize over these channels one for each x, the entropy of the average extensions. So this is clearly sufficient now. Follow from Schumacher conclusion. The question is it optimal? Unfortunately, we do not know. But if you regularize, which means that you take the state, row x1, row x2 through row xk, and then you take the extension of that thing. So this thing lives on A1, A2 through AK with a single additional system F to extend them. Multiply it to Px1 through Pxn. Sum over x1, xn. Look at the entropy of this new big ensemble over k copies with a single extension for each possible state. Divide by k, and then min over these maps, min over these extensions, I'll say it that way. And then take the limit, k goes to infinity. This rate is necessary. So we see the same theme. The distortion here is replacing the initial state by an extension. But it's only optimal if you consider potentially large blocks. Okay. So those are.
Sigma is chosen for every k individually or a priori? The extension is chosen a priori or at every level k individually?
At every k individually.
And then you get the optimality.
Yes. The good news is that I'm nearly done. So far I described 3 optimal results for vanishing error. The natural question for this talk is, of course, if you allow finite error, you reduce the rate. The quick answer is that if you look at global error, you measure the error for the entire n block. This is, if you look at the state, all n of them, we believe that you cannot reduce the rate. It's heavily proved for pure states. There's a lot of big progress for mixed state. It's what we call the strong converse. That says that if you reduce the rate by a little bit, the error will converge to 1. Exponential in the block size. If you consider instead per copy error, so what it means is that at the output, the real output is actually some big state Cn. You reduce to the first system, B1, you reduce to the second system, B2, and so on and so forth. Then you look at the state at x1, B1, and potentially the references. No, we don't look at the references. We have mixed state here. So we have, no, you just x1 and b1 on here. You compare with row x and a. That defines a local error. Take your favorite error measure. It can be trace distance. It can be 1 minus fidelity, and so on. You look at that local error, and you do it for every copy from 1 through n. Take the average. If you look at that average local error, then the answer is yes. You can reduce the rate by a certain amount. So let me write down the error definition. You want to keep this too. So this is the error that we're looking at, except you can be quite general in choosing the error function. This only need to be continuous. It is also funny because I write it as if there are two inputs. This one is fixed, so there's only one input to your function. If it is continuous in z, b, x, the other one I need is convex. And the last one is that it has to vanish for z equals to rho. I actually need the last condition, that your error has to be 0 if you actually have done the right job. Otherwise, we can't, our optimization will not be feasible, and you run into problems. So we need to add that condition there. Okay. So with that, then we got the following result. Before that, let me give credit to the people who have done this first. The pure state case has been first proposed by Howard Barnum in year 2000. And then there was a very crucial result that goes before ours by Leung Data, Min-Shui Shui, Mark Wooder, and Andreas Winter in 2013 on the pure state case. And I won't repeat the result here because the expression looked really similar to ours. They are actually different, but it has the same form. It has the same theme. So let's see. Maybe the fun stuff first before the boring stuff. There is something actually fun. So this is the result with Anil and Dave. It's recorded. So what happened was that we looked at the problem without noticing what Kobayashi and Emoto did. So that was kind of funny, but we found. But the results are incommensurate in some regard, luckily. But because of that, we actually looked into two distributions. So these aren't even quantum states. These are diagonal density matrices, two of them on d dimension. What we find is that if the error is about 1 over d to the 4th, then need the rate is at least log d minus 7. D is supposed to be large, so you can't compress much. If you take error, which is roughly 1 over d to the power gamma over 2, gamma is supposed to be a small positive number, take it as 1%. Then the rate is, there is a protocol that we wrote down that will do it for, roughly speaking, gamma log d bits. We studied the assisted setting at that, for that paper. But this is unassisted, this is assisted, so to maximize the gap. So if you tune your error as a function of the dimension, changing the power from 4 to gamma over 2, change the rate from maximum to something that is as small as you wish. So we really want to understand how it happens. And therefore we were doing this rate-distortion study. So then I'll write down the expression that we got. Just to tell you in the end, I still do not know how that. So what I want to know is the error as a function of the dimension. You can write down some feasibility result, but I do not know the best trade-off. And you'll see why after I write down the expressions. So by now I think we have this for long enough. So the best rate, assisted, with than D. We use a capitalized alphabet to emphasize that this is not small. It's min over something that I'll describe, half the mutual information between C and x prime R. This refers to the thing that I just erased. Initially, the state has an X and an A and a J. A is purified by R and X is purified by X prime. Evaluated on the state tau. And tau looks like this. We have the initial state psi. R X prime X A J. Then take A and J, run a channel over it, output C, and this is the state tau. Then take that state, evaluate the mutual information between C and X prime R, divide by half. And that's the rate that you can achieve. And it is, so first of all, this is achievable because of quantum state redistribution. Alice will literally just perform this on every copy, change the ensemble, transmit. If you're willing to then minimize over these channels N, from A, J to C, you get the optimal rate. Now this is a minimization that's constrained. You have to require that when you apply this map on rho AJX, is something that is close enough to, I'll call AX. So AJ goes, N, the channel N takes AJ to C. I should call this CX here. But it is the state that initially defines the ensemble. So the error of this cannot be bigger than D. So you have a constraint on what kind of distortion is allowed. The kind of mapping here cannot create too much local error. It should not create more error than you're allowed, but you can go up to that error. And then from that point onwards, you minimize over that channel to minimize the rate. And that is the optimal rate with the rate distortion theory. So we recover that thing, that distort, transmit. The most boring method is optimal in this setting. I'm still slower than I thought, so maybe I just verbally say some of the rest of the result that I want to show. For the, this is an assisted case, because we can do quantum state redistribution. Without entanglement for free, we will need to go through something similar to this, if it is visible. You have everything the same way, except you also allow the extension to suffer through a distortion. So that when Bob discards F, the average distortion of the K block is no bigger than D. If you do that, you do all that regularization, you get the optimal rate. You see, this is boring, right? It's promised. So what I want to mention is that, so what have we done, right? Why did it take us so long to finish this? There are a lot of continuity problems when we try to prove that you can't do better than this. Here, I don't even show the optimization. I'll use this one to explain where the problem is. If you look at this optimization, you think about it as a function of D. This function happened to be convex and continuous for the assisted case. So then our proof will go through. For the unassisted case, you can then define an optimization function that has a k in it, and then you take the limit of those functions to be the actual rate distortion function. So there, the continuity become a real pain to prove. They happen to be continuous. After 1 or 2 pages, and a couple of weeks, no, not quite, a week crying over Rudin, it can be proved. For distortion bigger than 0, if the distortion itself is 0, we can prove that for the special case when it is blind. We do not know what happened with general side information. So let's see. What else? So if someone has a good idea or better skill during the analysis, we would like to know if we have continuity of the unassisted rate at 0 distortion for general side information. This we do not. We actually say it in a comment in the paper that we have not been able to prove that. It ought to be, but we can't prove it. So then, there we, after all this boring but sweaty hard work, we gain some understanding of the problem. For example, we know that your redundant part of the ensemble does not affect your rate distortion function. So even with the rate distortion theory going on, the redundant part does not appear in any of the rates, which is reassuring, but it's not easy to prove without these expressions. So we did that. The earlier work that I did not mention, so I should say briefly, look very similar, but then there is no R because the states are pure, and the error definition is a little different. They include X prime in the error definition. So we do not know if those rates are the same as ours. It is possible because they have different error definition. You think if you use 2 different methods to calculate the same thing, you should get the same result. But no, these are 2 different things that we're calculating. So, what else? So, with all this work, I try to make my student calculate this trade-off using the optimization there. That's convex. The assisted one, so I should say one other thing. This function is convex. The constraint is a reasonable one that you write down. It's a convex optimization. So the assisted rate distortion trade-off is tractable in principle. He did not give me an answer. So I suppose it's not so easy. The unassisted one with the distorted version of that, promise me is useless. You have an expression, you may be able to prove something about it, but I don't think it is feasible to even compute much because it's not a tractable optimization for any sizable dimension. So then I want to end with an open problem, like a general discussion of a problem that I think kind of sit at the heart of what we cannot resolve in the end. So suppose I have the same system set up. I have a list of states. I know that there is a channel M that approximately preserve all of them. Epsilon is not so small. What do we know about the channel? This is not a boring question, but it is a very hard question.
It will depend a lot on how rich your row i's are, right?
That's right, that's right. The way we prove this result is to choose the distribution so that we can know something about it. We choose 2 states that heavily constrain the channel.
Give
you do exponential cardinality, it has to be close to identity, right? I mean, the standard perturbation argument.
But this is not vanishing.
Yeah, but for fixed epsilon, it's, I mean, less than 1, I guess, right?
The rich part is to let the error. Epsilon depends on the dimension.
Yeah, but that still, I mean, if the class of the row I is somehow a net somewhere, then you can say something.
That's right.
But if not, then it's, I think that even analysis problems, there are fewer questions have no possible to answer.
That sounds like bad news. But yes, I think just back to this example, two distribution on D dimension. It's not a particularly complex set of state. Just two distribution on D dimension. We still do not know what happened here. I mean, these are two nice things that we managed on the paper. Yeah, if anyone has has a student who want to think about, well, actually, shouldn't give it to a student. Yeah, I'll stop here.